Welcome to the second lab in our error detection and correction mini-series. In this lab, we're going to build a function for computing the parity of binary data. In lab 1, we computed parity on characters. So we compared a set of characters, ones and zero characters, and computed the parity on that. Today, we're going to build something more useful. We're going to compute the parity on the actual bits themselves. Okay, this lab continues from lab 1, but instead of checking the parity on bytes or ASCII characters, what the function that we're going to write is going to do is it's going to check the bits, okay, and check the parity on a set of bits, okay. So instead of, for example, checking the parity on characters, what's going to happen in this lab is that those that character array of ones and zeros is going to be packed into bits. So there's a function that is going to convert the byte form characters into an array of binary numbers, so a binary representation. So 1 byte is going to get converted to 1 bit, okay? Or 8 bytes are going to be converted into 8 bits, compressed down to a single byte. Just a reminder that one of the use cases for parity checking was for the detection of single-bit errors in memory subsystems, where you had 8 bits of memory, but where there was 8 bits of memory, you had an additional bit, which was the parity bit. And if there was an error, a parity error, you would get a blue screen of death, or a BSOD. And that's basically, your computer would basically shut down, and it would tell you that there was a parity error. And another reminder on how parity works, right? The system chooses whether it's going to be using even parity or odd parity, and the parity bit is set in order to achieve even or odd parity. So if you have even parity, then the parity bit is set to ensure that the number of ones in the bank, right, are even. Okay, so if there, for example, if there was 1, 1, 1, 0, so you'd have 3, if there are 3 ones, then the parity bit is set to 1 for even parity, so that you have an even number of ones, or it would be set to 0 to keep the number of ones odd. Okay, oh, and there's another example here where we have 8 bits of data, and the last bit is a parity bit. So here is an example that's for memory. Okay, so we have 3 ones. Okay, so for even parity, that P, or that parity bit, would be set to 1, so that you'd have 4. And for odd parity, it would be set to 0, so you'd have 3. Before you begin this lab, it would be very beneficial for you to review the following concepts from your Programming Fundamentals course, your C programming course. Bit manipulation in C. So some examples are setting bits with the OR, okay, so bitwise OR, testing bits with bitwise AND, bit shifting, as shown on the screen, bit shifting and assignment as shown, the conversion between hex and binary representation of bits. So just to remind you of what's a nibble is a single hex character or hex value. That's 4 bits, right? If a byte is 8, then a nibble is a small byte. That's 4 bits. The other thing you want to review is dynamic memory allocation using calloc. Okay, calloc sets everything to 0. Okay, initializes everything at 0. Malloc, it just allocates memory, and then free for freeing. memory that has been assigned. So just review these concepts because you're going to need them for this lab. In this lab, what we're going to do is we're going to start with the parity function that we had in lab 1. So you can actually copy that file over, the parity.h and parity.cpp. We're going to have a different main function, so download the mainline code from eConestoga. Okay. Now we're going to write a new parity function. The previous one in lab 1 was called parity on bytes. This one's going to be called parity. It's going to have the same sort of inputs. You're going to have, well, this time it's an unsigned pointer to a character array. That's buff. And then iBufflen actually is now the number of bits to consider in the parity calculation, not the number of bytes. Okay. So again, the buff is a pointer, so use it that way. It points to the very first memory address, basically, okay, of where the bits start, and there's going to be 8 bits in that at that location. Okay, the code is going to show you how to increment every 8 bits. You got to go to the next byte. Okay, so that's something that we're going to look at. Again, make sure to use buff as a pointer. Don't use array notation. The reason for this is because we're now looking at the individual bits, and there's no way to use array notation that way. Now, parity returns exactly the same as parity on bytes. It's going to return par even, par odd, or par error. Okay, so to recap, there's going to be a new main. So go in eConestoga and download the main for lab 2. In there, there's going to be a mainline code, and also a function called pack2bits. Now, this function is going to take the ASCII characters that come from the command line. So the same as in lab 1, right? The command line, they're characters that are supplied, and the pack2bits function is basically going to convert them into bits. Okay, so each character is a byte. It's going to be packed down into a bit. Okay, so if you have 8 bytes, it's going to be packed into 8 bits. Okay, in binary. The main and the function that we're going to write, the parity.h and parity.cpp, they must be in different files, just like in lab 1. You can't change pack2bits or main in any way. But I'd like you to review pack2bits and the main to see how your function is expected to behave. And pack2bits gives you sort of a background information on how to deal with bit bashing, which your parity function is going to have to be able to do. So it'll give you a review of that and show you some tricks basically on how to deal with these bits. Okay, so you want to update parity.h. Okay, you're going to keep the enumeration, the parity. You want to keep parity on bytes from lab 1, and parity, this is lab 2. Okay, so we want to add parity to this file. Okay, and your job is going to be to write parity. Okay, this is just a review from lab 1 for adding command line arguments in Visual Studio. Just right-click on the project name and click on Properties, and then go to the next slide. Okay, in debugging, you want to go to Command Arguments, and then you can add your command line arguments as shown here. Okay, we have an even, an odd. You want to probably put an error, so put some other character in there. Okay, so to start this lab, what you need to do is go into eConestoga, download main lab2.cpp, get parity.cpp from lab 1 and parity.h from lab 1. Okay, and what we're going to do is we're going to open up Visual Studio. Okay, create a new project, and we're going to make a console application and click Next. I'm going to call it Lab 2. Put it on the desktop and create. You don't have to put it on your desktop, but okay. Then what we're going to do is once it's created, we're going to go in here, get lab 2. We're going to take these files, cut them, okay, and go into lab 2 and paste it. Paste right there. Okay. This guy right here we don't need, but I'm going to delete it from inside here. Okay, so source files. We don't need this one, so right click, remove, and delete it from the project. Then right click on the source files, click add, existing item. We need main lab 2 as well as parity.cpp. Add that. Go to header files, right click, add, existing item. We need parity.h. Okay, so let's take a look at what we have here. So parity.h, I already showed you in the slide what you need to put into parity.h. You basically have to put the function prototype for parity, okay, which was already provided for you. And if you want, you don't have to here. The pack to bits function, you can put a prototype in there, but it's really not required because it's already in the main. So really all you need is this. Okay, this is the new function that we're going to add. This is lab 2. Okay, so once you have parity.h, you're ready to go. Parity.cpp, we have the parity from the first lab, and what I did, I just took the function prototype, pasted it here, and then opened up these brackets. Okay. So we have this. So this is parity on bytes. I'm going to minimize that. Okay. So this is the function we need to write. But in order to write this function, we need to have an understanding of the mainline code that's going to use it. So let's open that up. Open up main lab 2. And what you find is you'll find the pack to bits utility function, which we'll see in a second. I'm going to close that for a second. Okay. And then you'll find the main line. Okay. The first part of the main line is exactly the same as in lab 1. Okay. The function takes in command line arguments. argc is the total number of command line arguments, including the name of the file, the executable file name. Okay. argv is a pointer to all of the different strings in the command line. Okay, so you have the name of the executable, the first string, which is the sequence of ones and zeros, and then another string would be if it's separated by a space that we put there. Actually, let's go right click lab 2. Okay, I've already added this into my project, but if you go to debugging, actually no, it's not in this one. I'll add it. So we're going to do an even one. So 4 ones, maybe 2 zeros, space. Let's go, let's do 3 ones, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How's that? And then we'll do one that gives us an error. Okay, because anything that does not have a 1 or a 0 in it, this should throw an error. Right? So this one's going to be even parity. This one's going to be odd parity with more bytes than 8 bytes. Okay, and this one's going to be error. Okay, so remember, these are command line. The very first argument is really the name of this file, mainlab2.exe. Okay, so the very first argc, it's going to be have an argument of 1 all the time because the name of the file is the first argument. argv, this is a pointer to an array of strings. Okay, so argv at, let's say, 1 is this guy, right? argv at 2 is this guy. I'm wrong. argv at 1 is this guy. I skipped one of them. Should put an extra space maybe so you can see it. argv at 1. Okay. argv at 2. argv at 3 is this guy. Because argv at 0 is, again, the name mainlab2.exe. Okay. Let's say apply, and then say OK. All right. So this, a lot of this works the same way as the lab 1. Okay, we're going to have some variables here. Actually, we don't really use b-zeros, but anyway, we might use it in later labs. We have a couple things. We have a counter. We have RC. RC is an integer, but it's really of type parity. Parity is 0, 1. If I go to parity.h, parity, this is 0, this is 1, and this is 2. Okay, so I could have made it parity, but it wasn't that. It's an integer. Okay, it's no problem there. I is for our for loops. I-packed length is going to be the length. So basically in this lab, we are going to have this function, pack to bits, that takes a string of characters. Okay, each character is 1 byte, and packs it down so that each string character writes to a particular bit. Okay, in a binary representation. So each character has 8 bits. So if let's say you had 8 bytes, so 1 1 1 1 0 0 0 0, those would be strings that come from the command line. You could write all of those to a single byte, to 8 bits in that byte, right? So that byte would have 1 1 1 1 0 0 0 0, but those are the bits I'm talking about rather than individual bytes for each character. Okay, so pack to bits does this. We'll talk about that in a second. But I-packed length, okay, we need to represent, we have to say, okay, if I had 8 bytes, 8 characters, that's really going to convert to 1 byte, right? 8 bits, because each byte gets converted, becomes 1 bit. Okay, so our and really the whole point of this is that we're writing this we're going to write a parity function, okay, that operates on a character array, okay, but we're considering the individual bits rather than a character array of characters. Okay, so when we have this pointer points to an array of characters, but we're looking at the bits to compute the parity. Okay, and those bits were written by looking at a character array of 1s and 0s. It'll make a little more sense as we go. So let's just go. Let's take a look at what main does first. Okay, so this guy basically is when you converted from bytes to bits, what's the number of bytes you now need? This packed string, okay, is the location in memory where you stored those bits, okay, that you've converted. The bits we're looking at, where in memory we're looking, because we looked at a string, we have to put that string to write those the corresponding bits to some location in memory for those string 1s and 0s. I-bit is a bit. We may not use this. I-mask is a mask that for toggling or looking at individual bits within a byte. Okay, and I'm gonna, when we look at pack to bits, it's gonna give us a hint for why we need this mask. Okay, this mask is actually useful up here, in here. Okay, we may not need it in main, but it's there anyway. So what happens here? This code looks exactly like lab 1. Okay, so if you are confused about this, refer to lab 1. Why is it here? Is because the command line, the strings of 1s and 0s that I supplied when I right-clicked here and I went to properties, the parity should be the same. Whether I use parity on bytes or I use parity, which is going to be right over here. Okay, we should have the same parity, whether we're looking at it from, because the string of 1s and 0s is going to get converted to bits, and the parity is going to look at the bits when they're converted, the one on the bits, and this one's going to compare parity for those string of 1, 0 characters. But the parity should be the same. So that's why we include them both. Okay, so what's here? This just tells you the lab's 2 results. Pack to bits is the utility function, okay, that's going to take a string from the command line and write to a location in memory. The corresponding bits are going to be toggled to 1s or 0s. So if this is a character set of 1s and 0s, this is going to be binary 1s and 0s written to the memory location pointed to by b packed string. Okay, so this is the string. This is the length of the string, and what this is. So iPackedLint is when you've converted it from bytes to bits. You've packed it. How many bytes do you now need? So if you had 8 bytes in the original string, okay, if this was 8, then this would be 1. Okay. Now, why we supply the address of iPackedLint is declared here. Okay. So in order to write to it from the function, we're passing it by reference. We're passing the address, okay, of where the information that's stored in iPackedLint is, so that it can be written to by pack to bits. Okay, and then we can use iPackedLint inside main. Okay, and we're passing that to our function. Okay, so how does this work? We need this. We're going to need to know how pack to bits works. Okay, because that's going to help us to write. It's going to give us some hints for bit toggling. Okay, when we write our parity function. Okay, so anyway, pack to bits happens. We compute the parity. Okay, we pass the string, we pass the length in bytes, and then the output looks the same as we had in lab 1. Okay, the other thing is this function is saying if b packed string, okay, is not really if it's not null. Okay, so if it's not null, then basically this guy is going to return par even, par, sorry, not this guy. This guy is going to return par even, par odd. Pack to bits is going to give you the location in memory where the bits were written, unless there's an error. You know how that third input that we put in at the command line had an X in it? If it has an X, then pack to bits is going to basically throw an error, and this guy is going to end up being null. Okay, that's why it's written this way. Okay, so here it computes it, and then we free that memory location, and that's it. Unless there's an error, then it's going to be freed and packed to bits. Okay, so here's our output. We compute whether it's odd or even parity. Okay, and then if there's an error, it's automatically going to happen from this guy's going to be null. This one's going to happen. It's going to be null. It's going to free it, and it's going to go there, and then the program will end. So really, what do we need to understand? Well, we need to understand this guy in order to really be able to write this guy. So let's go up and look at pack to bits. How does pack to bits work? It takes in, you give it a character array. So this is the character array that came from the command line, buff. Okay, this guy has a length. Okay, a length of characters, and this poutlen is when you convert from, let's say you had 8 characters, that's 8 bytes, right? But really, when you compress that down, if you had 8 bytes, you convert it to 8 bits, you only need 1 byte. So if this guy is 8, this guy is going to be 1. If this guy is 9, this guy is going to be, it's 9 bits, but you actually need to reserve 2 bytes, right? Okay, so we're going to see how this is calculated. Actually, we could do it right here. See this, ioutlen? Okay, ioutlen, if we go down to the bottom, at the end, poutlen becomes ioutlen. Okay, so I could have just said poutlen equals this. Okay, I could have just done that. So I could have just said, instead of here ioutlen, I could have said poutlen equals this. What is it? What is it computing? Well, if this guy is 8, Okay? 8 plus 7 is 15. 15 divided by 8, this is integer division, is 1. Okay? If this guy is 9, 9 plus 7 is 16. Divided by 8 is 2. Okay? If it was 10, again, it would still be 2. Okay? So this formula basically just says that how many bytes do I need after conversion from string to binary, basically compressed down. Each byte is now represented by a single bit. Okay, so anything over 8, you got to go into the next bit. Okay, so that's what's happening there. This guy right here, what's P? P is a pointer to an unsigned car. A car is 8 bits. Okay, on any computer, it's 8 bits. This is a pointer to a location in memory. And what I'm doing here, you have to cast. Whenever you use malloc or calloc, you cast. This is a pointer to an unsigned character. Calloc is like malloc, except calloc makes everything 0. Okay, it allocates the memory and sets all of the bits. So let's say, I'll just give you an example. Or can I write over here? Okay, so if I have 3, 4, 1, 2, 3, 4, that's 1 byte. Okay, it set everything to 0. If I calloced, right, ILN, if this was 1, if I use less than 8, right, and if my number of strings was less than 8, then ILN is 1, and size of a car is 8. So there's 8. Size of car in bytes is 1. Okay, so this is 1. So I would have 1 size of 1. So I have 1 byte of memory. This is how many I have. This is what their size is. Their size is in bytes. Okay, because integers would have 2 bytes maybe. Depends on your computer, but some integers or on some machines it would be 2 bytes. So it would be 1, and then 2 bytes would be, instead of 8 bits, 16 bits. But in our case, we want 1 byte at a time. We want to have this to be it's a car, so it's 8 bits, so that this formula works. Okay, so we have it sets everything in. So let's say there's a memory location hex 23AC. Let's say is that memory location. Okay, and then this is what's stored in that memory. So P is this guy, and star P would be what's stored there. That's dereferencing. Okay, so let's stop that for a second. Okay, so hopefully that's clear. So we've allocated a space in memory. We've set everything with C. It sets everything to 0. Okay, in memory. What's pcur? Pcur. Okay, pcur equals P. It means that this variable here points to the same location as the memory location that we reserved. Why would you want to do that? Well, let's just say this is my first memory location. This is my second memory location. So P is always going to point to the very first memory location. Okay? pcur is used if you want to deal with the bits later on. Okay? So you have, you always want to keep in memory the starting where you started storing your memory, right? Where you started storing your information. But this guy is used for writing or comparing, right? Writing certain bits or looking at certain bits. Okay, so this guy can be incremented. That's what cur means, current. Okay, so that's why we want why you would want to do something like that. All right, what does the next one do? Well, what happens here is we got to walk through this buff, right? This string of characters. Okay, now so we need to walk through and we need to look at, are they ones or are they zeros, right? All right, so we're going to look at a string of characters and we're going to write to P or pcur. We're going to write to bits, corresponding bits. So bits are going to correspond to character 1 or character 0, and we're going to write. Remember, it was all set at 0 at the beginning, and we're looking for what we're looking for is if there's any ones in that string. Okay? If there are any ones in that string, then we're going to write the corresponding bits in pcur. So let me go here and just make this absolutely clear how this is working. Okay? So look, pcur point. Okay, we had p, right? Let me go here. Let me go here. At the beginning, I'll do the example of the two bytes of location. Okay, two bytes. I put a little space just so you can see it easily. Okay, but these are 2 bytes. This guy right here. So p points to. Maybe I'll do it above it. P points here. Okay, pcur points to wherever. Oops. Wherever we are. Pcur points to p. Points to this first byte, but it can also be moved to the next byte of reserved memory, right? We reserved this memory when we callocked. Okay? Well, in this calloc here. We reserved some memory. Here, let's just imagine we need 2 bytes. Okay? So we really, in order to need that, you need over 8 characters, but less than 17 characters in the string. Okay? pcur is going to be pointing either here or here. Okay. So what happens here? We're saying, okay, where's buff? Where's buff? Let me draw buff here. Let me put buff over here somewhere. Okay, buff is so buff points to the location where that string character, the 1 or the 0 is. Star buff dereferences that, right? So if star buff equals 1, okay, this is called dereferencing. So buff points to the memory location, okay, of a particular string. So let me do that actually. Let me say star buff. This is the very first one, but star buff has, I don't know, let's say it's a string of character. It's a, let me put it like this. Okay. I'm going to stop there because too many characters to deal with. Okay, so buff points to this very first character. Okay, but then there's other characters that will follow later. Okay, buff can be incremented to then point to this guy, incremented again. So buff points to, so here's buff, F is pointing, buff is the address here. Hex 0, 2, 5, 4, etc. That's buff. Buff is pointing. This is buff right here. Okay, buff is pointing to the memory address. Okay, where this 1 is stored. Star buff points to 1. It stores 1. Okay, and if I increment buff, I can make buff point to the 0, right? And then when I say star buff, then it's going to be the 0. Okay, so all I have to do is go buff plus plus, and it moves it there. Okay, so right now I'm going to leave it here for a second, just to show you. P is callocked. We reserve 2 bytes. They're all zeros because calloc sets everything to 0. Then what are we going to do? We're going to go through here. We're going to say, okay, we have this mask. It's a for loop. We need a counter. The counter has to stop when we have no more string characters to put in. So we do that. We have to increment it. We also have to increment our buff, okay, at some point, okay? So let's put that there just for now. I'll explain that a little bit later. But the main point here is we say if buff is 1. Buff right now is pointing here, right? Buff points to the memory location where this guy is stored. If I dereference it, star buff contains a 1. Okay, so if star buff equals 1, then we're going to do something. If it's a 0, we have no case here for 0. We do nothing. Okay. If it's not a 0, this guy right here, else if not, that means this is the error case. Like if we had that X that we put in, well then there's an error. So what we do is we free the memory location that we reserved and we return null. And this is a signal, right, that there's an error. And we handle that in main. If this guy is null, if it's null, then it's going to print out that there's an error and there's no issue. We've already freed that memory and we're fine. But okay. But the main point that I want to make is right here. What does this do? because this is going to teach you what to do in parity.cpp when you compute the parity function. So, star buff, if it equals 1, then we're going to OR equal whatever pcur. So pcur right here, pcur is, right now pcur is pointing at p. Pcur points at p. We haven't incremented pcur. It's pointing to this location in memory, right over here. Really, it's right here. It's stored at an address, right? It's 0 hex. I don't know. You can pick whatever you like. Is pcur, but star pcur contains this right now. Okay. So what are we gonna do? Star pcur is this. Star pcur really contains. Oops. Star pcur. Okay. It's pointing at this guy right here. Later it'll point to, well, dot dot dot. Later we can increment it to go here. Okay. So that's where this guy goes. He's pointing there. So what are we gonna do? We're gonna say, okay, if it's a 1, if the first guy's a 1, we need to write to this bit. How are we gonna write to this bit? Well, imask is now this, right? So what's imask? That is the hex representation. What's the binary representation? So imask equals what? Okay, so we say it's hex, it's 8, 0, right? So binary, that's this. That's 8, right? 2 to the 0, 2 to the 1, 2 to the 2, 2 to 3, that's an 8. And a 0 looks like that, right? So what's the result of this or equal to this? Now that's going to be the new pcur. So the new pcur equals 0 or 1 is 1. And the rest are all zeros. Right? Right? So that's what's happening here. That's what this pack to bits is doing, right? So now, if I do it again, right, it at 0, okay, there's nothing for 0, so it's not going to do anything. All it's going to do, okay, is it's going to the next line is going to take imask, okay? So it's gone through this guy. We get to this step. It's not a 0. Okay, the first one was a 1, so it's not a 0. Then we increment imask. This is our new imask. So what's our new imask? Go back here. Imask equals, well, this is a bit shift, right? Bit shift. This was imask, so we got to shift this bit to the right by 1. So now it becomes a 0, 1, 0, 0, 0, 0, 0. Okay. Then we go here. imask does not equal 0. This if handles the case when you've shifted the bit 8 times over and you get back to 0. What that means is you need to reset the mask, okay, to be this, so that you can take this. Then what you're gonna do is you're gonna move to the next byte. Okay. So what you're gonna do is once you get 8 over, right? Once this gets 8 over, right? You've gone. This imask has shifted 8 over. Now you got zeros on your mask. You've already looked at all the bits here, right? You've already written all the pcur bits based on the bits from the string. Okay, that means let's say I had more than 8, right? I don't know. I want to keep going here. Let's go like this. If I had 9, for example, right? 9 characters to write. 1, 2, 3, 4, 5, 6, 7, 8. I don't know. 9. Okay, then I got to go into the next bit. When I write, right? When I write eventually, okay, when I'm writing from here, from what's here, I'm writing to this memory location. If I get more than 8, then I have to go and write to the next byte. Okay, that's what this is doing. Okay, if you reach 0, that means your mask, this 1 has shifted over 8 times already. You've written all the bits in pcur. So that means you need to go to the next byte. So you reset the mask to look at the first. So your mask is now going to be 1, 0, 0, 0, because you want to look at the very first bit in the next byte. That's what that does. And pcur, okay, we're incrementing pcur So we're shifting this over to the next byte. Okay, so that's what's happening there. Okay. Okay, so that takes care of anything over 8 bits. Okay. All right. So anyway, we've shifted over. Here we had a 1. Then we go back the next time around. We got this 0 to contend with. Well, it's not a 1. It is a 0. We just shift iMask over again. So now we're going to shift all we're doing here is shifting iMask copy. We did it already. Sorry. We shifted 1 over. It was a 0. We did the comparison. Sorry, we got to go back. We got to do it here. We got to shift it again. This is going to be the 3rd time around, right? After the first time around, right? It was a 0. We shifted it over. So that means that it's going to be this, right? And now we're going to say iMask. Now we're looking at this guy. So this guy is a 1. Okay. So what's pcur? Pcur is this, or equals this. So now the new pcur is going to be, let me go here, is going to be this mask and or this. So that's going to be control copy, control paste. Right? This is the or equal operation, right? Or equal. And the result is going to be this or this. It's going to go to this. Okay. So at the end of the day, you can see that these strings of 1s and 0s get written to the memory location pointed to by pcur, right? And p is just storing the first, right? The first memory location, the first byte, right? It's pointing to this guy because pcur can move to the next one, and it's used for writing to those bits. But basically, what you see is that these strings will be written. So 1, 0, 1, 1. Basically, I'll just keep writing it, and then 1, 0, 1, 1, and then 1, 1, 1, 0, 1. So it'd be 1, 1, 1, 0. Well, if then what I'd have to do is go to the next one, right? And then start writing on this first bit, like that. Okay, that's how this whole thing will. So basically, you go from bytes, ASCII strings, to bits. Okay, that's what this does. Okay, and that's how this whole function works. So now, with this in mind, okay, we use or equal for writing. Okay, and if we want to read bits, we're going to use and, not and equal, but and. Okay, that's used for reading. So these are the two pieces of information that we need in order to write our parity function. So let's save this. Let's go over to parity and just look. How are we going to? Let's look at what we did here. What we did was we found the sum of a bunch of. We have bits. We need to compute the number of ones, right? So look, we have this. This tells us if the number of ones is even or odd. So we can borrow this. Let's copy that. We need this. Okay. Okay. So we have a sum. So we need to int. We need I sum. Right. We need that. We probably need a. Well, we should set it to 0 because that's what we have up here. We probably need a counter just like we did up there. Okay. But now we need a loop. We need some sort of loop. We need to loop through the bytes. Okay. Well, we need to loop through. We need to look at each individual byte and then go one at a time through the bits. Okay. So what we need is okay, let's go with a for loop. Let's say I equals 0. Okay. I less than, well, I buff len, at least that, right? We know this is how many bytes. Okay, this guy's keeping track. And I don't want to increment, because look, I don't want to increment every time through the for loop because I want to look at each bit inside that byte. So I'll leave the incrementing for later, right? Like basically, when do I want to go to the next byte is if let's see, if something happens, then I will I plus plus, right? Then I'll increment, but I don't know yet what that is. Well, when is that going to happen? Well, I'm ask. We saw this before. If it equals 0, right? And we haven't done the mask yet. We haven't said. Then we increment. We go to the next bit, like we saw in the previous example. When iMask reaches 0, right? And so what we should do really is go. So we should say int. Now go back to here and just get some, right? So iMask, where was I? What did we? Yeah. So we said unsigned car iMask. Let's do the same thing. So unsigned car iMask. So copy. And then we actually set at the beginning of the loop, we said iMask equal to that. We could do that if we wanted to. Let's just do this. Unsigned car iMask. Okay. So we have that. And what we should do is we should set it equal to 0 hex 80. Let's do that there. Okay. Let's do that. Okay. And remember that this is, just to make sure that everyone's clear, this is 1, 0, 0, 0. Right? This guy is going to be used to look at each of the individual bits. Okay, what's passed? It's buff, right? Buff is the thing we're looking at. Okay. So, when mask gets to 0, we also have to go to the next character, or the next byte in buff, right? This is the case. If we have more than one byte in this loop, then we have to buff plus plus as well, right? Okay. If iMask equals 0, we also have to, like we did before, reset, right? 0 by 80. Okay. So when we're going to be going through each of the bits in a byte, right? This is how many bytes we have to go through, but we got to go through all the bits. But okay, so there was that part where we said iMask, and then we said we bit shift by 1. So we're going to do that too. We saw that up here, right? We're going to bit shift by 1 regardless, right? We always want to bit shift by 1 because we want to do 1 bit at a time. So this is not going to be an if. But what are we going to do? We need to check the individual bits in buff. So let's say here, let's do an example. We have iMask. What is it? It's 1 0 0 0. Right. Okay. So that's iMask, and let's just say we have some sample. Let's just say that the thing that we're looking buff. Let's go to buff. So star buff is what's stored, right? Equals what? Let's just go and just get a number. Let's just play around with this. Okay. So let's go with 1. Let's just make it really simple for ourselves, like this. Like that. How's that? Or we'll just do that. Okay. So this is what's in buff. So what are we going to do? We want to know how many. What are they even number of 1s in buff or odd? We know that it's even, right? So what does our algorithm have to do? Well, we have to see if we have to count somehow, right? We need to do something with sum, and we have to show is it a 1 or a 0, and then increment something. So we have something we got to increment, right? So we say if something, right? Then we need to increment. Oh, what did I? Why is it not aligned? This guy should be with that guy. Yeah. Make sure. Yeah, it's good. Okay. So then we increment. So I sum plus plus, right? So if this is a 1, because we want to do the same thing we did up here, right? We want to sum. So now it's not if star buff equals 1. We can't look at the specific buff. We need to say if iMask and star buff. Oh, there we go, right? So if So if this guy and this guy, so what's that going to be if I AND it? So this is AND, right? So this guy, if I say AND, will become, this will become 1 and 1 is a 1. So if there's a 1 in buff, then the result, and this is 0 by 80, right? This is non-zero. This is going to be a true value, right? But if it was, okay, so that's that. So that's true. So if I say if star buff, right, and I mask, okay, so this number is truly, then I sum is 1. Now what if I get to, okay, that's fine. Okay, then so then I sum it up. Otherwise, I don't increment the sum. I sum, what is it? I set it at 0. So I started it off. That's good. Now, what if I get this other case where, so I've incremented I mask. So I mask now. I've incremented sum. So sum went up. I could put the number here if it makes more sense. So I sum now equals 1, right, for that one. Now what if I go back and, okay, so now I've incremented it. Now I move the I mask up. So the I mask is going to go like this. So basically now I'm checking this bit. So what is it? 0 and 1 is 0. 1 and 0 is 0. 0 and 1, 0. They're all zeros, right? So this is 0, 0. This is falsy. So then, because this is falsy, 0 is false, is falsy. This is not gonna, ISUM is not gonna increment in that case. Okay. So what we've seen here is, I mean, I kind of gave away what it was. If you use AND, this is how you poll your bits. Okay. So here we're polling the bits. This polls them. Okay. And then this guy just says, okay, if it's non-zero, then increment the sum. Right. Okay, and then I mask gets shifted. Now, if I mask gets shifted all the way to the right, then we're going on to the next bit. That means we need the next bit. So I mask gets reset. I gets incremented so that the for loop knows when to stop. This is how many maximum number of bytes, okay, that we're going to use after conversion to byte-oriented binary numbers. And then buff goes to the next. Why buff goes to it goes to the next basically byte in the string that after conversion. This is the one that gets converted after it's converted to bit oriented string. And then the rest is the same as before. Okay, so this should work very nicely. Let's save it and let's run it and see what happened. If everything goes right, then our results should match the first lab. Okay, are we hitting an error? Did we hit, okay, so the first lab works right. We got even, odd, error. We're not getting any results here. So, what do? Well, we have to go back and check to see what's causing the error. Let's see. The thread exited with code 0. Perhaps there's something that is being missed. Here's the issue. I didn't assign. I didn't assign it by 1. Right? I mask must be equal to bit shift and then assign. Okay. So that's what I did wrong there. Okay, that's clear. That's fine. No problem. Let's save and rerun. Is that the only error? Yes. Okay. So let's compare even, odd, error, and then, okay, this is unable to allocate space. Why that is because, look, in pack to bits, okay, what happened here was that it's not equal to a 0. It's not a 1 or a 0. So we freed the space and return null. When you return null, over here, if it says here, see, if this is not null, then do this. Otherwise, this is the output. Okay, I could have said par error if I wanted to, but that's how this was written. Okay. I hope you enjoyed the lab, and I hope you learned something about bit bashing and working with certain data structures and algorithms, as well as looking at pointers, how they work, referencing, dereferencing, pass by reference, all of these concepts to review what some of the things you've learned in previous years.